Okay, so I realized this mirrored camera thing. I didn't say what the bound is, so it's if the pattern doesn't occur, then you probably won't ever see anything, any substring whose hash matches the hash of the pattern. So you get n plus n with high probability if the pattern doesn't occur. If the pattern does occur, then you have to decide, am I going to check it, and various things like that. So it gets a bit complicated. You can find it online. I just want to say, so what can you do with Karp-Raban? You can do actually a lot of things in Karp-Raban, but there's this thing called multi-pattern matching, which is you get a bunch of strings and you want to make one pass over the text. So so you have P1 equals ALA and P2 equals ABA and P3 equals BAR and P4 equals WHY. And P5 equals something else, and P6 equals bat, and P7 equals cat. And so now you want to make one sweep over the text and figure out if there are any occurrences of these patterns in there. And so you can do this with a variation of Knuth-Morris-Pratt called Aho-Korasik. Aho, I think, was also Canadian, Finnish-Canadian. Alfred Aho, I think he was Canadian. I think he was from Sudbury or Sault Ste. Marie or something like that. Wikipedia will know. And so you can do that, and this build, so you build an automaton that now it's a bit more complicated. You can do multi-pattern matching versions of lots of things. You can do all kinds of magic with multi-pattern matching. I'm just going to say so what's the magic of Karp-Raban? Well, suppose that you have length of the text equals, say, 1,000,000. No, let's say 100 million. Okay, so and number of patterns. So we have 100 patterns of length 1,000 each. So you could say, okay, maybe the text is on disk or something, or somebody's going to send it to us. So we actually don't have to worry about storing it. We're just going to stream over it. So we ignore the space for the text. So we're going to in Aho-Korasik, we would build an automaton, and then we just keep that automaton in memory, and we stream over the text. And so our workspace is actually the space of the automaton. But that's actually going to be about as, in the worst case, it's going to be about as big as the combined size of these patterns. So it seems like we're going to need about 1,000 bytes for each pattern of length of 1,000 characters. So we're going to need about 1,000 bytes for each pattern, and we're going to need 100,000 bytes, which is not so big. It's 100 kilobytes. We could make it that. We could make these numbers bigger to make it sound more interesting. But we're going to need 100 kilobytes to store all these, just to store, keep in memory what we're looking for. Well, can we do better? And the answer is yeah. With Karp-Raban, if we just want to say if where there are occurrences of some of these patterns. And we don't want to check. We just want to trust that if the chances are billions to 1 that we make a mistake, then we're willing to put up with that. Then what we can do is hash. Oh, the other thing is, for Karp-Raven to work in this case easily, you can do it otherwise, but in order for it to work easily, it's length 1,000 each, exactly 1,000. We want the patterns to be of equal length. So what do? We take the patterns, we compute their Karp-Raven hashes, which is a number in the range 0, which is 0 to well, p minus 1, where p is this prime we've chosen. So it's a 64-bit number, because p is at most 2 to the 64 minus 1. So it's a 64-bit number. And so we just need to store 8 bytes for each of these. So now we're just storing about 800 bytes instead of 100,000 bytes. And now we run over the text, and so we just keep these. We have a hash table or some sort of membership dictionary, and we run over the text with this sliding window of length 1,000. And so we need, for the sliding window, we need to remember what's in the sliding window, so that when we receive a character, we know that we can delete the character that's leaving and throw it away. And we use like a couple of thousand bytes instead of 100,000 bytes. And the chances of making a mistake, if we do this properly, are still billions to 1. So I didn't finish. I'm not going to go on too long because I promised that this would only take, I'm up to 7 minutes. I didn't say that I showed you what the chances are for a particular substring of length of t of length m being a false positive, and then it's very small. You can drive it down exponentially small, and then to say, okay, so what's the chance of there being any false positive in the text? And then you use that wonderful thing from when we analyzed quicksort called the union bound. Okay, so you just multiply by the length of the text, by the number of positions you're considering, which is n, and it doesn't do very much. So you still end up with the chances of making a mistake are billions to 1. So that's kind of cool. So in our remaining 2.5 minutes, we'll just write down, we hash each pattern. We keep only the hash values in a membership dictionary. So what would we actually use? We'd use a hash table. The only problem with that is that we have hash values in a hash table. It sounds a bit confusing. But you could also use an AVL tree. You could use whatever you want, such that given a value, you can check if it's in your set. And then we run the sliding window of length 1,000 over t. Remember, we don't have to, we're receiving the characters of t 1 by 1, so we're not responsible for storing all of t. It's this streaming model. I don't know if you've heard of it. It's very popular at the moment. It was super popular about 10 years ago. It's still super popular, I think. It's not what I work on most of the time. Keep track of the hash of the window. So again, whenever we want to slide the window to the right 1, we have one character coming in, so we take the current hash, we subtract the first number, we multiply by, well, if we're doing base 10, we multiply by 10 and add the incoming number. We're working base 255, so we multiply by 255. So this is called rolling. So the Karp-Rabin hash is a rolling hash. It lets you slide the window over 1 doing a constant number of arithmetic operations. And then at each step, we check the dictionary to see if the Windows hash is in there. So the idea is we don't have to store all the patterns. I mean, maybe we could store them on disk or something, and only if we get a hit, only if we find some substring of the text that says, yes, we get the same hash as one of the hashes, the patterns, but we don't know what that pattern is, so maybe then we have to go and look it up. But actually, if we just want to know, are any of the patterns in there, and we're willing for there to be a mistake, if one of the patterns is in there, we will definitely say yes. And the chances of us saying yes when it's not in there, we can do this such that it's billions to 1. So this is actually, when I said it's a bit magic, probably a little bit, I'm up to 12 minutes, I'm sorry. You can actually look through a massive text when you don't even have enough memory to know what you're looking for. But you can tell if it's there. You can have, well, actually, you can have a lot of things, and you can't even, well, that's what I meant you're not even looking for one thing, and you can't remember what you're looking for, because you have to, actually, if you get really fancy, you don't have to have enough memory for the sliding window. You can do this trick called sketching, which some friends of mine do, but it's super complicated. You can sort of say, is the thing I'm looking for there, and you can't even remember, or any of the things I'm looking for there, and you can't even remember the things you're looking for. And that sounds weird, doesn't it? I mean, so I should also mention that Karp shared the Turing Award with Cook, because Cook, there was Cook and another guy called Leonid Levin came up with NP completeness, and then Karp showed that things like clique, so Cook showed that SAT is NP complete, and Karp showed that clique and independent SAT and hitting SAT and like 21 other famous problems, ham path, Karp was the one who showed in a paper the next year, he showed that stuff is all NP complete. So like it seems there are only like a handful of people in theoretical computer science actually. No, there are thousands, tens of thousands of us, but a lot of stuff is done by a few people. And Rabin is sort of one of the big names behind the idea of non-determinism, I think. I quote Rabin. I think he also got the Turing Award for something. So he was also involved. I think he was one of the people who defined non-deterministic finite state machines. I'm not sure. I should have checked that before doing this lecture. Sorry. So, okay, I wanted to, it's 15 minutes. I'm sorry. I'm going to cut this short. So that's as much time as we have for string matching. I don't think I even did this in the fall semester. I've probably included, I've misspoken, I've been a bit vague, I've skimmed over stuff really quickly. But it's online, you can find out about it, and I don't think anybody ever tries to do this in one lecture. I might put one question on some assignment about some of this stuff. But it's close to what I do, closer than most of what the stuff we've done. Okay, so cheers. Sorry about all this.